Okay, so if here is the table, and this is your mirror on its side, and here's the mirror holder thing. So are we okay with my perspective there? So you're looking at the side. So you put an object in front of the mirror. So here was the object here. Call that the object. And what did you see? What's the fancy word? The image. And it was, and I made it all dotty dot because it's not really there, right? Isn't that the image? And then you measured a distance from the mirror to our dot right here, to the object. Let's call that the object distance. So DO is object distance. What about the distance from the mirror to the image? What do you want to call that? Yeah, DI, image distance. Can we come up with a rule for this plane mirror? What's another word for plane? Flat. So what's the rule? What do you think the rule is for where our image would be located? Equal. So how about a DO? And one more is equal to DI? Okay. All right, so that's our little rule for plane mirrors, kind of plain, huh? Now let's do another little activity. All right, so now we're looking at a bird's eye view of there's the line, and your mirror was sitting on top of it. Now my hope was that you put one object here, you took your second object, and your eyeball was like over here. So here's your eyeball. I'll give you some eyelashes there. Okay, so your eyeball was looking, and you covered up the image of the first one with your second object there. And then you kept it covered up, covered up, covered up, covered up, covered up, and made another dot. And then I asked you, hey, why don't you connect the dots? 1 and 2, 2 and 3. Like that. Now, if I was drawing this, I would probably make it all dashy lines because there's not really a line there. We were just connecting two things that we were looking at. Anyway, so this ray of light, we have traced a ray of light. Light from the room or from the sun or whatever hits an object, and there's light rays scattered from all different sides of it. That's how we can tell, we can see shadows and things because the light's not coming straight to your eye there, or there's less light being reflected, and then you can tell like the shape of an object. It's really cool how that works out for us. But of all the light rays, we were looking at one particular light ray, and the one that goes into the mirror, and that is called the incident ray. That goes into the mirror. Now, there's a protractor in your bucket bin of science. What did you notice when you measured? Could we measure the angle that it hits the, like right there? What's the angle from the mirror to the incident ray as compared to the mirror to the, and this is the ray that leaves the mirror and comes to your eyeball. Anybody want to take a guess as to what that's called? The reflected ray, that's right. And when you were measuring, did these look similar to each other? All right. So usually, though, for light, we are going to measure the angle to the normal. Normal? What's the definition of normal? Perpendicular to the surface. So what do you think about these two angles right here? If my picture was perfect, what should they be? They should be equal. So I'm going to call this one right here my angle of incident, and this one right here my angle of reflection. And what do you think we could we make a rule up for that? Yeah, they're equal. So theta I is equal to theta R, and that is called the law of reflection. All right, so if we take a spherical circle, haha, that was an oxymoron. Okay, no, not oxymoron. It was redundant. It was dumb. Ignore me. And maybe here's the sunshine. Where's the sun compared to us? Is it close? Is it far? It's really, really far away. And if the rays of the sun are so far away, they're almost coming in straight. Where is all of that light going to bounce to in this mirror? To a place we call the focal point. This happens, thus we name it. So there's a point, and that ray, the incident rays, will bounce off and go through the focal point, through the focal point, through the focal point, through the focal point. And it turns out, how cool is this, that focal point, even though my picture is not very pretty, that focal point is mathematically located at half of the radius. Whoops, that's not a 2. Half of the radius.
Just from the edge?
Mm-hmm.
Towards the center?
Yep. So when I had it as a full circle, if we found the radius of that circle, this picture is just not very pretty right now. All right, so now let's look at your drawings that you've got there. So I'm going to draw another circle for myself, but you don't have to do that because you've got the handy little problems there to look at. And there should be a focal point that's marked on there for you. Is that correct? And then an object way over here to the left. Is it like an arrow? Okay. So remember that light rays, light from the sun, from a lamp, from whatever, hit an object and they bounce off in all different directions. All different directions. Scattered all over from the surface. We're going to look at 3 of those bazillions of rays to make a ray diagram. The first one, we're going to look at a ray similar to one coming from the sunshine that is parallel to the diameter, or the principal axis, if you want to call it that. Has a name. So that's the incident ray. And this is where you can use your colored pencils if you want to. There's some in the basket. And then it bounces off and goes through the focal point. Now your second ray is going to be exactly opposite of that. So if a ray goes parallel and through the focal point, what if we traced a ray that started from the top of the object, went through the focal point, and then it would be reflected parallel? So far, so good? Now my center of curvature is the next one. All right, so then the next one is going to go through the center of curvature and then back on itself. And the center of curvature should be twice the focal length. And mine's not quite perfect, but there should be my center of curvature. And then back on itself. Twice the focal point. It's the very center of the circle, yeah. So, where all of these rays cross is where the image is formed. Now, when you are outside the focal point, so when your object is outside the focal point, that was when you were holding it at arm's length, how did you appear? Look at yourself again. How do you appear in that concave mirror? So then this image right here is what we call a real image, because it's actually formed there. That's how the image of your finger when you're poking at yourself in the big giant concave mirror is a real image. It's upside down. The fancy word is inverted. And instead of magnified, if you want to refer to its size change, we can use the word reduced. We had parallel and through the focal point. Then we had through the focal point and out parallel. And then our third one was through the center of curvature and then back on itself. I just didn't draw a little arrow.